What's up, sim scientists? I'm going to make this video to go through the rest of the practice test topic review. So kind of a broad overview of a lot of topics that you need to be refreshed on, ready to go when it comes exam time. So first off, we're going to talk about the periodic table and the trends of the periodic table. So the trends of the periodic table, the three of them that are on your sheet, they're all based on two things that happen as you go across the periodic table from left to right, and then down the periodic table from top to bottom. Okay, so we got this cute little periodic table here. It's great with color code for all the specifics and everything like that. So let's talk about what happens when you go across the periodic table from left to right. So when we're thinking about this, we're going to stick in one period. We're going to go across one period. So if you're in one period, like let's say we're in the third period with sodium here. So you have an atom or atoms that have the energy levels 1, 2, 3 energy levels. Now, as we talked about in the periodic table section of the study guide, as you go across any given group, like if we go across the third period, or any given period, so we go across the third period here, everything in the third period has electrons, valence electrons in the same energy level, the third energy level. So when we add electrons here, we're adding them to this energy level, to this ring only. So this would be sodium with 1 valence electron. This would be magnesium with 2 valence electrons. This would be aluminum. This would be silicon, so on and so on. So what else is changing as we go across the periodic table? Well, this number right here is going up by 1 with every element you go over. All right, what is that number called? The atomic number. Atomic number, which is the number of protons. So as we go across the periodic table, we're adding a proton and an electron. From left to right, every time we go to the next element, we're adding a proton and we're adding an electron, as long as it's neutral. The protons and electrons will equal each other. So we're adding a proton and we're also adding an electron. But all of these electrons in this period we're adding in the same energy level. They're all in this third energy level here. Okay, so the effect that the nucleus has on this energy level is getting stronger as you go across. Just think of the ring as one thing. Whether there's 1 electron in it or 8 in it, this ring, the outermost ring, is one thing. So this nucleus, as it gets stronger, is going to pull this ring towards itself more and more. So as you go across a period, like the third period here, these nuclei are getting stronger. Aluminum has a stronger nucleus than magnesium. Silicon has a stronger nucleus than aluminum. Phosphorus has a stronger nucleus than silicon, and so on and so on. It's getting stronger and stronger. And the stronger it gets, the more it pulls the outer electrons towards itself. It's holding them more strongly. So it's holding them with more force. The stronger the nucleus, the harder it holds those electrons. So it's pulling them towards itself, and it's holding them in a stronger way. And we'll see why that's important when we talk about the trends in a second. Okay, so that's for when you go across a period. Now let's talk about when you go down a group. So periods go across, groups go up and down. I'll white that out. Periods go across, groups go up and down. So now let's talk about if you're going down a given group. So every time we go down, when we're drawing our little atom here, in the first period, right here, you have 1 energy level. The period number out here, 1, 2, 3, 4, 5, 6, 7, equals the energy level. All right, so for period 1, n equals 1, n being the energy level. For period 2, n equals 2, energy level equals 2. And we see that when we do our electron configuration because the number out front is the energy level. So 1s, 2s, 3s, 4s, and so on and so on. So as we go down to a new energy level, we're adding a ring every time. So every time we add a ring, it means the previous ring is full of electrons. There's a bunch of electrons, and the atom is spreading out, essentially. The electrons are getting further and further away from the nucleus. All right, so when I go from hydrogen to lithium, I add a new ring. When I go from lithium to sodium, I add a new ring. When I go to sodium to potassium, I add a new ring. I go to potassium to rubidium, I add a new ring. So let's look at these trends themselves and what this means. So on that, every time I add a ring, the effect that this nucleus has on the outermost electrons is getting less and less because there's electrons interfering with that effect, and the ring is just getting further and further away, the outermost ring. So the valence electrons are way out here now, and there's a ton of interference from the shielding electrons. It's harder for this nucleus to have an effect on that outermost electron. Okay, so let's look at how this affects these trends. So first of all, we have atomic radius. Oh, dear Lord. Radius. Okay, so this is, technically it's the 1/2 the distance between the nuclei of two atoms when they're bonded together. So if you had two atoms, nucleus, atom, atom, so two nuclei, it would be 1/2 of this distance between the two. I think it's easier to think of as the distance in one atom from the nucleus to the outermost electrons. Now, technically, we can't see where the outermost electrons are at any given time, so we can't really measure it. It's easier to measure if you have two of the same element. You can measure from nucleus to nucleus and cut that in half, and you'll get the size of the atom. But essentially, in theory, we're talking about measuring from the nucleus to the outermost electrons. So that's what radius is, the distance from the nucleus to the outermost electrons. Now, as we look at the periodic table, like I just said, as we go across from left to right, these nuclei are getting stronger, they're pulling the electrons closer, so radius is decreasing. Okay, lithium has less of an effect on its outermost electrons than fluorine does. Fluorine's pulling them harder, so the size is getting smaller. Now, as we go down the periodic table, we're adding another ring every time, first energy level, second, third. Every time we're adding a ring, this is getting bigger and bigger, and this nucleus is having less of an effect on the electrons. It's not pulling them tighter. So as we go down the periodic table, atomic radius is increasing. Okay, that's radius. Okay. I'm just going to try to ignore that this time. Now let's talk about ionization energy. So this is the energy it takes to make an atom an ion. Okay, so it's the amount of energy it takes to remove an electron from an atom. Energy it takes to remove an electron from an atom. So this directly depends on how strong the nucleus is, how much force the nucleus has on the electrons. So as we go across from left to right, what's happening to the nucleus's effect on the electrons? It's increasing. The nucleus is getting stronger. Therefore, ionization energy increases because it takes more energy to take away an electron from one of these stronger atoms over here than it does from the weaker atoms over here. These strong nuclei are going to hold it tight, the electrons tight. These aren't going to hold it as tight. Now, as we go down the periodic table from top to bottom, and we're getting these elements that have a ton of rings of electrons, they're way, way, way out here, it's hard for these to have a strong effect on their electrons. And something like francium, which has 87 electrons, that means that there are 86 electrons between the nucleus and the outermost electrons. That's hardly going to have an effect. That nucleus is hardly going to have any effect on the outermost electrons. So ionization energy is decreasing as we go down the periodic table. It takes less energy to take away those electrons. Okay, lastly, let's take a look at electronegativity. Electronegativity. Okay, so this is an atom's ability to attract electrons while bonding. So this is like in a water molecule, why oxygen draws the electrons towards itself. The stronger the nucleus, the more it can attract electrons. So as we go across, our nuclei are getting stronger, higher atomic numbers in the same energy level, so electronegativity is increasing. As we go down, for the same reasons as the last one, we're getting a ton of energy levels, a ton of electrons between the nucleus and the outermost electrons, so that it is decreasing here. Okay, so anything over here is going to draw electrons towards itself more than something over here, and as you go down, they're drawing even less than from above. Okay, so that's the trends of the periodic table. You should be able to answer all the questions on your study guide from that. All right, now let's talk about nuclear reactions, or nuclear decay, whatever you want to call it. So first, let's talk about alpha decay. Okay, so alpha decay consists of a helium nucleus. A helium nucleus, aka an alpha particle. And that looks like this. You have, okay, so this up here is what? The atomic mass. And right here we have atomic number. So atomic number tells us the number of protons. So there are 2 protons. Atomic mass tells us the mass of an atom. Electrons have essentially no mass, so it's the protons plus the neutrons. If I have 2 protons and 4 protons and neutrons total, that means I have 2 neutrons. Okay, so that's what makes up an alpha particle, 2 protons, 2 neutrons. That means it has a 2+ charge overall. The 2 protons make it positively charged. Okay, and it has low penetrating power because it's kind of big and slow. Okay, so 2 protons, 2 neutrons, total weight is 4 atomic mass units. Okay, so if I'm looking at something that's undergoing alpha decay, like let's say, let's pick an element here. Let's say selenium undergoes alpha decay. So if selenium undergoes alpha decay, that means it's going to shoot out one of these. It's going to shoot out an alpha particle. By the way, as far as your notes go, you should pretty much have all this written down, and then for what the rest I say, you can try and fit it somewhere or somewhere else. So let's say selenium shoots out an alpha particle. If it shoots out an alpha particle, what is it losing? 2 protons, 2 neutrons. Okay, so selenium on its own would be Se 7934. Okay, it's losing an alpha particle, so it's going to become that alpha particle. The total atomic mass is going to go down by 4, so it's going to be 75, and the number of protons is going to go down by 2, so it's going to be 32. If my number of protons changes, is it still selenium? No. Okay, so now I have to look what has an atomic number of 32, germanium. So now this is germanium. If the number of protons changes, then the atom itself changes. So that's alpha decay. Beta decay. Beta decay. So in beta decay, you lose a beta particle, which is an electron, basically. So we have this, 0, -1. Okay, so this is an electron. The mass of this is essentially 0, but it's about 1/1840 AMUs, so very tiny mass. Your mass is not changing. And it has a -1 charge with moderate penetrating power. So it's going faster, smaller, and can penetrate a little bit. So when something undergoes beta decay, what essentially happens is that you have a neutron, and you can kind of think of a neutron as something that has positive and negative charge within it. So overall, it's neutral. This neutron is going to shoot out a beta particle, which is shooting out an electron. So if we consider this something with positive and negative charge in it, and it shoots out negative charge, what's left? Well, it becomes a proton. So when you have beta decay, let's look at selenium again. So if this selenium, instead of alpha decay, was undergoing beta decay, so it's giving off a beta particle, now it's gaining a proton, right? Because one of its neutrons is changing to a proton. So the AMU, the atomic mass, doesn't change because neutrons and protons weigh the same. It's shooting out something that's essentially massless. So the mass isn't going to change. But because it is gaining one proton, the atomic number is going to change. So now I look at selenium, it's gaining one proton. So I know the mass is staying the same, and it's gaining one proton, so the atomic number is becoming 35. So that would be bromine. So now instead of selenium, I have bromine. That's what happens with beta decay. Okay, now the last kind of decay is gamma decay. Gamma, so you have the little symbol for gamma. You get 0, 0 because it's massless. Massless. This is electromagnetic radiation with no mass, no charge. Okay? So, therefore, there's going to be no change. If selenium underwent gamma decay, it would still just be selenium, just like it was before. There's no change when gamma decay happens. But it is very dangerous, and it has very high penetrating power. Okay, now lastly, for radioactivity, we talk about fusion and fission. So fission is when you get a bigger atom. Okay, so it has a lot of neutrons in it. It's kind of almost ready to blow up. So you shoot stuff at it. You keep adding neutrons to it until it gets so big that it splits into two parts and gives off a lot of energy. Okay, so fission is a splitting of a nucleus into separate fragments with a lot of energy. Gives off a lot of energy. Okay, fusion, on the other hand, fusion is when nuclei combine to produce a nucleus of greater mass. So we have two nuclei combining to make a bigger nucleus. That's essentially what you need to know. Fission, you're going to see splitting. Fusion, combining to make something bigger. In fusion, you have two smaller nuclei combined to make one nuclei of greater mass. Okay, I think I'll end this video here because I need a break. And then I will complete the rest of this study, guys. Thanks so much for watching, guys. Smash like.